Hi, my name is Bryant and I'm a development engineer for Texas Multicore Technologies. In this video, I will be using SequenceL to write a simple program to demonstrate SequenceL's ability to automatically take full advantage of multiple cores in a multi-core environment. I will also demonstrate SequenceL's ability to utilize an arbitrary number of cores specified at runtime. With SequenceL, we can actually change the number of cores we would like the program to utilize after the code is written without recompiling. The number of cores can even be an input from the user. In this video, I will not be focusing on how to program in SequenceL. The point of this video is to demonstrate the relative ease with which a developer can write parallel code using SequenceL. The program I'll be writing in SequenceL is a simple prime number counter. It will count the number of prime numbers which are less than or equal to a given input integer. So let's go ahead and get started. First, I'll make a new SequenceL project, calling it primes. Here, you can see that Eclipse gives us the two key parts of the SequenceL project, the main C++ driver and the main SequenceL file. I'll start by writing the SequenceL code. How exactly this code works isn't important at this point, but the isPrime function determines whether the input integer is prime, and the primes below function counts how many primes are less than the input integer by using an index declaration in the let body as a filter. You'll notice that the isPrime function is very similar to the definition of prime numbers. The ease of code readability is another important feature of SequenceL. Next, we'll specify the intended use and move on to the C++ driver file. The C++ driver file will read in two arguments from the command line, the number which to count the primes below and the number of cores to run the program on, allowing us to decide at runtime how many cores the program should use. Here we can read the values directly off the command line. I won't perform any input sanitation. The first thing to do is call sl_init with the number of cores. This initializes a SequenceL runtime. When a SequenceL function is compiled, it produces a C++ function of the same name prefaced with sl_, the last two arguments of which are the number of cores and the output destination. So next, we call sl_primes below with the input off the command line, the number of cores, and result. Here there is also a call to sl_done, which cleans up the runtime. I'll also add a timer so that we can track the effect of varying core counts on performance. And finally, we can display the results, and that should do it for the code. Now we can build the project and try running it. This computer has an Intel i7, which has 4 physical cores hyper-threaded to 8. I will be using the Windows Performance Monitor to watch how SequenceL makes use of the cores on my system. To get started, I'll use 0 for the core count. This instructs the SequenceL runtime to detect the maximum number of cores available on the system and run on all of them. You can already see that the program peaked out at 100% core usage across all 8 of my cores. That very small amount of code is already capable of making full use of all the cores on my system, but that's not all SequenceL can do. I can now back the core count off to 1, instructing the SequenceL runtime to use at most a single core. Once that's finished, you can see that takes about 14.7 seconds to run. Now, if we move that up to 2 cores, what we hope to see is an approximately linear speedup, with the 2-core runtime taking about half as long. Once that's done, that is in fact what we see, with about a 7.8 second runtime. Moving up to 4 cores, the trend continues and we get about a 4-second runtime. We can move it up to 8 cores, but you'll notice that the speedup appears to taper off some as we move into the hyper-threaded cores. This is often the case with multi-core applications on hyper-threaded systems, and SequenceL allows us to easily test on these various core counts to see what's optimal for our application. To further illustrate the power of runtime-specified core counts, we can also run this program on some odd core counts, like 3 or 7. This is often hard to do in manual parallel development. But here we see SequenceL automatically taking full advantage of those core counts. To see just how well SequenceL was able to automatically parallelize this program, here I've plotted these runtimes at these various core counts, as well as the ideal runtimes given perfectly linear speedup. This shows us that this very small amount of code was able to very efficiently make use of the various core counts on my system. What I've shown today is the making of a relatively simple program in SequenceL, which is capable of automatically taking full advantage of all the cores on my multi-core system. But more than that, I am able to specify the number of cores to use at runtime. In traditional parallel development, a developer must choose the number of cores they would like their program to take advantage of and program directly for that. With SequenceL, the developer can, once the code is written, experiment with different core counts to find the optimal number, factoring in the overhead of things like hyperthreading and operating system interference. Thank you for taking the time to watch this video. If you have any questions or comments, feel free to comment on this video or contact us via our website, which is linked to in the video description. If you're interested in learning more about SequenceL, be sure to subscribe to this channel.